Constant acceleration. Well, up until now, we have been dealing with situations in which our velocity was constant. In the last lab that you did, the dry ice puck down a ramp, you saw that as the puck fell, it picked up speed. So it changed its velocity. So what we're dealing with now is a situation where the velocity is no longer constant. So we're going to have to change things, and we're going to have to add variables. When we had a constant velocity, we were able to define everything using three variables: delta x, delta t, and v. And because it was constant, this didn't change, right? So now we're saying it's going to change. So instead of just having one variable, we're going to have to deal with a couple of variables. And we're going to define v naught to represent the initial velocity, and also v. And we'll call v the final. This is just a notation that a lot of textbooks use, and we'll use in this class. Before, these three variables, delta x, delta t, and v, were enough to define it. Now, v is not good enough because it changes. So it's going to be delta x, delta t, v naught, v. And then we're also going to add this new variable, which is the rate at which the velocity is changing, or a, which is acceleration. And just to keep in mind, all of these ones that I'm highlighting here are all vector quantities, okay? So really, technically, every time you write them, they should have a hat. Honestly, nobody does. So don't worry if you forget to write the vector sign, as long as you keep in mind that direction matters. And so that will help. So I've listed them here on the handout. The variables that we are going to use in this part of the course are all these 5 variables. And it's important just to get used to them, to see them. We're going to come back to them time and again. So here we have a formal definition of acceleration. And it is that the acceleration of an object is referred to as the change in velocity, or delta v over delta x, the change in velocity of an object with respect to time. So v naught minus v minus v naught, the final velocity minus the initial. So if something is speeding up, its final velocity will be bigger than its initial velocity, and it will have a positive acceleration if we depending on the direction we define. We'll talk more about this later. So just looking at units in this example, the units of velocity are meters per second. The units of time are seconds. So we end up with this weird unit, which is a meter per second, or a meter. And so if you kind of put these two together, you end up with a meter per second squared. What this means is a velocity changes by a certain amount of meters per second every second. So for example, if I said something had an acceleration of 1 meter per second squared, what I'm saying is every second, the velocity of the object is changing by 1 meter per second. So at time 0, it might be going 1, and then at 1 meter per second, then 2 meters per second, then 3 meters per second. You can see that it's getting faster and faster each time. And because it's getting faster and faster each second, it covers more distance or displacement each second as it travels. So we're going to do a bunch of problems, and we're going to come back to that idea over and over again. All right, so there's a couple of things we are going to assume. When we say the word uniform, what we mean is we mean constant. So uniform means constant. So if I say uniform acceleration, what I mean is constant acceleration. Now, before, when we were solving constant velocity problems, we had an equation that sort of combined these 3 variables together, right? It was delta x equals v delta t, or you could have written that as v equals, another way of writing this is v equals delta x over delta t. Either way, these are to the same equations. Again, this isn't good enough anymore because we have a changing v. So we need a new set of equations. these equations can be derived, and they will, I think, over time in this course, especially when we get into graphing motion, we'll learn more about where these equations come from. But today, and in this problem solving activity, I'm going to just give you the equations, and I'm going to tell you what they are, and we're going to use them practically to solve problems. So there's a few assumptions we're going to make as we go through this. So we're only going to deal with constant acceleration. So where the acceleration is constant over a given time. So if we're talking about an interval of time, we're just going to assume that acceleration is uniform. If anything changes, if the acceleration changes, if it stops and then like turns around or something, that might you might need to break your problem up into more than one section. So for the time interval we're dealing with, the acceleration has to remain constant. And we're still only dealing with one-dimensional motion. And what I mean by 1D motion is it's just back and forth on a straight line. Okay, we're not going to turn any corners, so we're going back and we're going forth, either up, down, left, right, north, south, east, west, but we're not going to, like, for example, go west and then south. Okay, we're not going to do those kind of problems just yet. We'll get to them, but they involve a little more, a little bit richer math, vector math, and we're going to talk about those later. So because we're dealing with 1D motion, we handle the direction. So if it's going forward or backward, we handle that with a positive or a negative sign, a positive sign or a negative sign. And this is like what we did in the previous problems, where if you assign a direction to be positive, automatically the opposite direction is negative. So we'll keep that in mind as we solve the problems. So assigning a sign convention is a really important part of getting these questions right. So then these equations are going to sort of be your best friend for the next, I don't know, maybe 4 classes, and you're just going to keep using them over and over again as we go through the course. You do not have to memorize them. I would give them to you on a test or any kind of quiz that we had, but I think you'll probably end up becoming really familiar with them. And like I said, they can all be derived by different means, but I'm just giving them here to you for the sake of brevity, I guess. But for example, this first equation, we can derive this equation because we know that acceleration is the rate of change of velocity with respect to time, which means A equals V minus V naught over delta T. I just rearrange this to make it a more convenient form. So delta T times A equals V minus V naught, and then rearranging this again, V equals V naught plus A delta T. Just rearranging it, and you can see that this equation is this equation in the circle. Okay, so each one of these can be derived by different means. For the rest of them, we're going to derive all of these using graphical methods, and we'll do that later on in this class. So these 4, you're just going to have to take on faith for now, and then we'll show where those come from when we get into calculus. Those of you that are taking calculus, CAS calculus, probably have already derived these equations, and we will do that as we go through the course, but you need to have integral calculus for this, and I don't want to introduce that before your math teacher does. So a note on free fall. What I want to say about this is just we will get into more detail about, again, we're going to get into more detail about free fall, but free fall is a perfect example of uniformly accelerated motion. When something falls to the earth, it increases its speed at a uniform rate, and that rate is 9.8 meters per second squared. We often ignore air resistance, which sometimes reduces the acceleration, but unless otherwise stated, we are going to assume that if something is falling through the air, it's doing so at a rate of 9.8 meters per second squared.